Hello, I'm Claire. I'm an undergraduate at ANU, and today I'll be giving a talk on improving garbage collection observability with performance tracing. This is joint work with Steve Blackburn of Google and ANU, and Zixian Kai of ANU. So let's start things off with a fun fact, or maybe not so fun. Debugging garbage collectors is really hard. Luckily for us, we have a bunch of tools to help, and we can group these approaches into kind of a few main debugging approaches. So the first type is sampling, and generally this looks like some quasi-periodic interrupts where we observe snapshots of the program state. And so this might be like looking at some call stack samples and then identifying hot methods and their calling context. The second main approach is counting, and this is really an aggregate method. So it might be looking at, say, the number of times an allocator slow path gets called, or the proportion of a heap that's live after a collection. The final type is logging, and generally what happens is we pick a metric set, and then we just dump a bunch of information about these metrics to some log files. So what's the problem? Well, it turns out all of these methods have quite a lot of limitations that are particularly problematic in the context of GC debugging. So the issues with sampling come from its inherent statistical approach. Sampling suffers from a lot of sampling bias. Because we're taking like these periodic interrupts and then looking at what the program state looks like then, we get dominated by an average case. And so it's really difficult to capture tail performance. It also means that if we really wanted to try and capture these tail events, we'd probably have to take a huge amount of samples. And even then, we might not really be able to see anything. Sampling also only gives you statistic correlations between events, and so we can't actually draw proper conclusions on causal links. And for GC, this is quite problematic because work is constantly being dynamically generated. You know, say you do an object graph traversal and you look at some nodes, you might discover more nodes that you have to look at. And so we want to be able to trace things back to root causes. The main issues with counting are just that it lacks detail in general. We're collapsing a distribution down into an aggregate number, and we also lose a lot of temporal info. So, you know, it's, for example, a lot less helpful to know that 15 GCs happen than exactly when each one started and ended. The final one, which is logging, has some problems caused by the need to pick a metric. So because it's generally just very impractical to try and log everything, we need to have a good idea of where the root cause of our performance problem might be, because then we can pick some metrics. And this often involves having quite intimate knowledge of our code base. It's also quite inflexible because every time we want to change a metric or look at something new, we need to modify our code base. And normally your log files are quite unstructured, so then we might have to write some parsers as well. And this might be an example of a log file. So what's the solution? Well, there is actually one debugging approach called tracing, which is quite common in general systems debugging, but remains largely unharnessed in GC debugging. We're going to make the case today that it is very powerful and flexible and really nicely complements the dominant methods that we just talked about. So the key idea with tracing is that we're capturing a dynamic trace of a program's execution. And this is done through these things called trace points. Trace points can look like non-inline function calls and returns, or things that we statically define into our code. And they're either active or inactive, and that's something that you toggle at runtime. Trace points can also take arguments, which will be important later. So here's an example of a trace point. So the probe call in some Rust code. And when they're inactive, they're instrumented as no-ops, which means they have basically no overhead. This is really important because it allows us to compile a set of trace points into key parts of our code base, and we don't have to really worry about performance implications. To actually activate a trace point, you write some tracing logic that attaches to it, and that's how you determine what data actually gets recorded. And then when we actually encounter an active trace point, a bunch of information gets packaged into a trace entry, and then you I guess in the kernel side, the tracing logic is compiled to some bytecode, which then performs your user-defined tasks. And what happens there is your trace entries basically get processed in temporal order. So because all of your tracing logic is actually programmed at runtime, tracing decouples the actual trace points from the tracing logic. So we can reuse the same trace point to analyze behavior against metrics that we get to choose at runtime. So for example, up here, the same trace point is used here to measure the distribution of your work packet sizes. And then again here by swapping out some of your tracing logic to measure the total number of work packets. And then again here for a distribution of the root packet sizes. And all of these metrics were chosen after compilation. Because of this kind of design, tracing doesn't suffer from a lot of the problems that logging, sampling, and counting suffer from. So unlike sampling, tracing attaches context to events. And this means that we get to pick the level of abstraction that we can debug at. Tracing also, because it records kind of every single event that happens, it's really easy to capture rare events and then trace through these temporally to really clearly see causal links. Unlike logging, we also don't need to know a fixed metric set beforehand. All we need to do is have a set of very useful trace points and then just write some tracing logic to attach to those and pick whatever metrics we want later. Another note is that tracing outputs are quite structured, and so we don't have to instrument parsers, which is nice. In our work, we use MMTK, Memory Management Toolkit. This is a framework for building collectors, and it allows us to combine these low overhead trace points with a modular GC design. This is super advantageous because it means that all of the advantages of tracing really readily translate to all of the supported language bindings and collectors. But I will also note that a similar sort of approach should benefit any sort of collector implementation. So before we discuss the debugging approach a bit more concretely, I want to give some background on how the collectors in MMTK work. So collection work is done by a bunch of GC worker threads that execute work packets, which are basically just like packets of lots of work items. So these work items get grouped into packets by work type, and then these packets get bucketed by preconditions. So one key feature of the design is that these work packets are self-contained. So they normally have like a pointer to some code that will tell you how do you process this packet and what preconditions do we need. And then these work buckets get executed serially. So as an example, you have two worker threads here, and the different colors are like different buckets. So they might execute some work packets and then produce some more work packets dynamically into your local pools. And then they'll just keep grabbing from the global pool. When they run out, they'll grab from the local pool. And when they run out of that bucket, the bucket closes and a new one opens. With that kind of work packet design in mind, we can now identify a lot of critical points in the MMTK codebase. And these are the ones that we've pulled out. So the first one, collection start and end, lets us look at the stop the world collection time. The second pair of trace points lets us look at the time we spend in the allocator slow path, and they fire about every 64 KB of allocation. The third set, bucket opening, just records when the bucket opens, and because these buckets execute serially in a fixed order, then we can also know how much time we spent in each bucket. This fourth set of trace points records things at the granularity of work packets. So we can look at things like the work packet type and how much time we spent in the work packet. And this last one is a bit different to the previous four in that it's a really important special case. So the process edges function is the one that completes the transitive closure over the object graph. And this set of trace points gives us information about that. So things like the number of edges we visited and the packet size. In total, this was 14 lines of Rust code, which brings us to our first claim. Tracing is inexpensive. In a software engineering point of view, we wrote 14 lines of code, but also from a performance point of view. So on the board here, these are some of our overhead numbers. I'm not going to go into detail, but I'm happy to come back to them. The main thing I want to highlight is that there was essentially no overhead when the trace points are inactive. So we can compile these things into our code, leave them off, and then not worry about that affecting our performance. Today we're going to talk about one of the case studies we did, and this was using tracing to examine the scalability of the transitive closure stage of garbage collection. This is something that we're really interested in because the object graph trace typically dominates our collection time, and so understanding points of poor scalability will help us improve the overall collector performance and scalability. Just a note on methodology, we used OpenJDK 11 with MMTK and the Decapo benchmarks from the 2023 Chopin Dev branch, and we had two different architectures. So when we were looking at scalability, we picked out 4 different metrics, and these ones were scalability of the transitive closure. So this just looks at against like against a one-threaded application, how much quicker is your transitive closure getting when you double the amount of threads. And in order to measure this, we use the bucket open trace points. The second metric is the distribution of work packet sizes. And in order to measure this, we use the process edges trace point. This is something that's important to understand because the actual work packet size distribution can very much change how well things scale. So, if you have really large packets, then you're much better amortizing fixed costs, things like global synchronization and packet fetches. But if you have much smaller packets, then they're a lot easier to distribute among your threads. This third metric is quite similar, so we're looking at the root packets now, which are the ones that prime the closure. And the motivation is very similar to why we want to look at general work packets. And the final one is an explicit measure of load balancing. So generally, if we have scalability issues, they come in the flavor of like load balancing or some form of contention. And in this case, we're looking at how is work distributed among our threads through time. And so we can actually look at, are threads getting starved out? Are things being load balanced nicely? In this talk, we're just going to focus on these 2 for time, but we do have results for the other 2 in the paper. So if we look at closure scalability first, these 2 plots are the same plot, but with different things colored. So the lines on the plots are different benchmarks from the Capo suite. The x-axis is the number of threads, and the y-axis is the factor of speed up that we're getting. And I guess the red dotted line as well is perfect scalability. So the first thing we might notice here, if you can look at the really faded lines, is that scalability is quite workload sensitive. What I've done here is pulled out 2 that didn't scale very well, and we're going to dig deeper into these because a lot of the time workloads that don't scale well can tell you a lot about potential areas for improvement in your collectors. So next we'll look at work distribution through time, and we've got the 2 that didn't scale very well, FOP and LU search, and Tomcat is up the top just as an example of good load balancing. And here tracing makes it extremely clear visually that we have a load balancing problem in these 2 poorly performing benchmarks. So let's zoom in a bit. This here is just looking at FOP, same picture as before. The 2 arrows indicate when buckets are being opened, and we can do that using our bucket opening trace point. And we can see that we've basically got one thread executing a bunch of work packets in some sort of linked list situation. It doesn't look parallelizable, and it's all in one bucket. And so we annotate that, and it's finalization. So by using tracing, it's now abundantly clear that the source of the poor scalability in this benchmark is serial execution of finalization. Next, we can look at LU search, and we're going to zoom in on that little slice in red there, because, yeah, I guess just to give some context, what we can see here is we've got load balancing problems as well, and there seems to be 3 threads that just keep working, probably on some sort of linked list situation again. And so we'll just look at one of them and then figure out if it's kind of the same problem for all 3 threads. So if we zoom in on that slice there, we notice a really long list of work packets. And using the process edges trace point, we can annotate these packets with their size. So we know actually each packet is the exact same size. They all have 25 items in them. We also can run this over a bunch of collections and notice that this happens every single collection cycle. And so we hypothesized that there's some sort of unparallelizable long linked list structure happening. At this point, tracing has helped us narrow down a problem that we probably normally wouldn't even notice, down to like an issue with some sort of linked list structure. And doing a quick type dump tells us that every single packet here corresponds to a search query file which LU search failed to close. So basically, we've identified an application bug. And in fact, after we put the bug fix in, the scalability issue appears to have resolved itself. There are 2 points here that I want to highlight. The first one is just how flexible this tracing framework is. So, for example, we used the same process edges trace point to look at the distribution of work packet sizes, and then we used it again to look at the distribution of root packet sizes, and then we used it again to look at load balancing. And all of this we did on a running binary without recompiling. So I guess the point here is that it's super flexible in that we can examine a series of different problems without even knowing beforehand what we actually want to interrogate. The second point here is how it amplifies subtle performance issues. So things like the subtle application bug in LU search and the serial finalization issue in FOP probably would have gone unnoticed otherwise. But in tracing, it was just so visually clear what was going on. To wrap things up, GC debugging is just notoriously tricky, and all GC developers really need to rely on a collection of powerful tools. But the issue that we have right now is that a lot of collectors lack support for tracing, and instead we rely on things like sampling and logging, which simply are just not quite sufficient. Our work here shows that performance tracing really nicely complements the existing debugging approaches, providing low overhead observability, flexibility, and amplification of subtle issues in ways that the dominant state of the art can't. Thank you.
Any questions?
I always connect tracing with large trace files. So how much data do you collect? Is it a problem? Is the amount of data that you collect a problem, or was it no problem at all?
So what we use is an existing tracing framework called eBPF, and it essentially provides like a lot of code already for handling things like histograms and stuff. So actually storing those is almost nothing. So the data itself that we produce is not a problem.
And a follow-up question, could you somehow use similar approaches that you used for monitoring garbage collectors for normal user applications too? So sampling, like method calls or whatever. Could you just transfer it to normal programs?
Yeah, I think that like similar tracing approaches could be just generally very helpful in all sorts of systems debugging. I guess the advantage that we had here was a very modular collector design. And so that means that you put a set of trace points in, and then you're getting observability on a bunch of things at once. So, if you want to translate this idea to something else, it might involve a little bit more instrumentation.
Okay, thank you.
Thanks.
So you mentioned eBPF. Why did you choose eBPF? Won't this force you to constantly switch between the user level and kernel level to do, so on any trace point, you actually do a transition, context switching, right?
Yeah, so I guess, actually, maybe for a bit of context. So eBPF is a tracing framework, and the idea is like you write these BPF programs and you target like a sandboxed in kernel, and then that responds to user space events. So the main like overhead that you get there is the context switch, right? And in our case, we picked eBPF just because of how flexible it is. And we did a lot of evaluation, which I have here, and it's also in the paper, on the actual overheads. So if we go back to this slide here, so this slide here is the actual like performance overheads that we had. So the TP columns are like unattached trace points, so that's just the cost of compiling these things. OB is like the open bucket trace point, and P is process edges. And we can see that, like, for example, for the open bucket trace points, like, we're looking at like fairly negligible performance impact. And even with process edges, you might have, say, a collector overhead of about 12%. And in a lot of contexts, when you're debugging, it's not like negligible, but it's small enough that we consider it okay.
What were the inspirations of this work? Where did you get the ideas?
I guess the main inspiration was just that debugging a lot of like GC things within the group was very, very tricky, and you're lacking a lot of observability. Generally we're looking at like taking samples, doing like a bunch of ad hoc re-engineering and whatnot. And then someone in the group had done some work, I think maybe with Google, that used this like eBPF tracing. And we thought, oh, this is like really cool. We could apply this to our GC stuff and hopefully get rid of all of the annoying ad hoc engineering that we're doing.
All right, let's thank the speaker again.